My name is Nathaniel Jones. I'd like to thank you for joining this webinar, a knowledge representation and reasoning framework for building applications by Parastu Delgoshai. This webinar is hosted by the IBIPSA USA Research Committee with the goal to share new ideas from research to the building simulation community. If you have questions during this webinar, please type them in the chat window. At the end of the 45-minute presentation, I will unmute our audience on Zoom for a discussion with Parastu. Next slide, please. AIA Continuing Education credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. And now, I would like to introduce Parastu Delgoshai. Go ahead.
Hi, everyone. Thank you, Nathaniel. My name is Parastu Delgoshai, and I'm a research engineer in building energy and environment at National Institutes of Standards and Technology, known as NIST. I would like to thank all of you for attending this webinar, and I certainly hope you learned something new from this presentation. I also would like to thank the IBIPSA USA Research Committee and the organizing team for giving me the opportunity to share our work with the rest of the community. And as was mentioned, if you're here and would like to receive credit for this course, please send an email to info@aiaeb.org. So here's the course description. Hopefully you have seen it before signing up for this webinar. Now I would just would like to remind you the learning objective of this webinar. Hopefully by the end of this course, you will understand how W3C, which is World Wide Web Consortium Standards and Tool, can enhance building analytics. After that, hopefully we'll learn about some existing semantic schemas that can be used for buildings. Understand how those semantic models can be developed for different building applications, and finally understand how these semantic models can be queried to provide information. So here is our vision for this work. We would like work towards buildings that can make sense of data. And in a few slides from here, I will talk about specifically what that phrase means. But for now, I would like to think about it as a building that can think of like human beings, the way that we understand knowledge, the way we can kind of infer based on an existing knowledge and kind of produce new knowledge. We would like our applications to have that capability. And if we have that capability of reasoning through knowledge, then different building analytics applications such as energy auditing, commissioning, fault detection diagnostics, smart grid interactions, indoor air quality is going to be tremendously enhanced. So that's the goal that we're kind of targeting. Also, the problem that we're trying to solve here is that, as I mentioned in the previous slide, the emerging applications such as fault detection diagnostics, the commissioning, they need access to building system design, sensor data, control information, so different sources of data. But also at the same time, a lot of these data are contained in drawings or naming conventions that are coming out of your building automation system. Documents, sometimes this data is part of a maintenance staff knowledge, and by the time they're retired or gone, that knowledge is not available anymore. And the manual process of finding and mapping that data for different building application is a very major barrier for commercialization of a lot of these applications. And as a result of what I just mentioned, we would like to have a way of machine interpretable description to solve this problem. So that's the recipe that we are offering. And the solution we see is bringing context to data. And I'll go through an example what exactly that means. So I would like you to assume that you have a piece of information from your building automation system that is a sort of a combination of characters and some numbers. And we as human beings, when we look at this string, we will try to decode it and say, okay, well, maybe this is a zone temperature and some floor. But how about in a case that we would like our computer application or a software application to understand what this piece of information data is? For example, to be able to ask, what is it? And then the answer is, okay, it's zone 3 temperature. Or to add to the ability to ask about the unit of the measurement and say, okay, this is in degrees Celsius. Furthermore, that application may also need additional information, such as where's this zone located? Is it, and the answer could be on floor 4, or which VAV box applies to this zone, or what air handling unit is serving to this zone. So these are different additional questions that the application would like to know the answer for. That is going to help tremendously in either its diagnostics or making a decision. So how are we going to achieve that? How are we going to bring context to the data? The approach that we're proposing here is to apply W3C, Semantic Web Ontologies, and standard to create formal models. And that's the key point, formal models. And then those models can represent building system components, the relationship between them. As I mentioned, the VAV is related to the zone in various contexts. And then we're gonna store control and data points to those models and be able to ask questions from those models. So that's sort of the picture. To give you a little bit of a background, prior studies have shown significance of knowledge representation in field of building analytics, automation, and control. Semantic web technologies promise new opportunities for efficient management of information and knowledge in the built environment. And also, there are ongoing current efforts in industry, academia, and standards that are just focusing on establishing semantic models for the built environment. Oh, I love this quote by Plato that says a good decision is based on knowledge and not based on numbers. So let's go back to my first slide that I was talking about what it means to make sense of data. So a lot of the times applications are just working with data, raw measurement data. It could be numeric value, it can be string values, it can be enumeration of different kinds. So those are just raw measurement data points. When we label that data and process that, we're gonna get information. For example, we're labeling data, okay, so this 28 is a temperature or a specific kind of temperature, and the unit is in degrees Celsius, or the pressure is 225 Pascal. So at this point, a lot of the building applications are focusing on the data or information. Now we want to have the pathway to go beyond that. And that's where we categorize similar labels into concepts. For example, if we have measurements for different rooms, we're going to introduce this concept of room. If we do have different devices, different types of fan, we're going to categorize these different fans and create a concept of fan. And after we kind of categorize the similar labels into concepts, then we're going to define the relationship shown here in a gray solid line between these concepts that are shown by dashed line. So to kind of form a graph, you can think of this whole dashed line as one node of a graph that's related to another node through the solid line. And that solid line is the relationship between these two concepts. And for example, here we're going to say fan A, if this is a concept of type fan, is related to this concept of zone. So that's how we're kind of building the graph. And the important part is the wisdom part. Now, if we have these graphs, these formal models, then we can run inference on them and then be able to infer something that was not explicitly asserted in the graph. That's shown in like this orange line. For example, we can infer that filter X is clogged and is causing a reduction in airflow rate, that is also causing that the set point temperature in room A is not being met. So that's the key part, that we're going to work from data to wisdom, and we want our applications to work on these two layers and have more abilities for decision making. Now, I would like to ask to kind of for me to get a sense of who the audience is. I would like to ask you to answer to the poll by identifying what's your knowledge level about semantic web. Option A is you have never heard of it. Option B is you've heard of it, never used it. Option C is I'm waiting to see how existing ontology will be used for different building applications. So that means you already know a great deal, and hopefully this presentation won't be so boring for you. So please go ahead and take a moment and respond to the poll. And if someone can let me know about the result, I would appreciate that. It's going to be interesting to see what the answer is going to be. Do we have the results? Sorry, I'm just seeing the screen sharing. I don't have a way to see the results of the poll.
Right, we had about 47 of people respond that they've never heard of it. 25% heard of it, never used it, and 28% are waiting to find out how the existing ontologies will be used for different building applications.
Wow, that's a big number. Well, hopefully this, for those of you who already know this, hopefully this webinar won't be too boring. But I also need to go through a great deal of details about the first category. So thank you for that. Okay, well, for those of you who are in the first category, I need to kind of set the stage for where I'm going to talk about later in this webinar. So semantic web is an extension of current web, the web that we all use and to do our businesses and work, but it provides meaningful information to the machines, and that's a key point. As I mentioned in my first slides, we want the machines to have the ability to understand knowledge. They're better suited for integrating data from heterogeneous sources. And all the data is stored in a graph, in a triple format. And this graph is a key point, as I mentioned in my previous slide. So we have this node that's a subject in this triple format that's related to another thing, we'll call it an object, through a predicate. Also, that other thing can be a literal. And this literal can be a string, a Boolean, an integer, and any other data type that you may have. So again, the key point is these graphs are connected to connected nodes. So for example, if we consider this concept of human, Jane is an instance of a human that's related to another instance of a human, Dave, through the relationship of has friend. Also, concept of Jane, instance of Jane is also related to another instance of human, Mary, through the relationship of a has supervisor. So subject, predicate, object is the sort of the pattern here. Now, I would like to test you, for those of you who are not familiar, to tell me in this simple semantic graph, how many predicates do we have? And I would appreciate if you can take a moment. So this simple graph, I would like to know how many predicates do you see? And as soon as I know the answers, I'm going to move to the next slide.
So we had no one saying one. 83% of respondents said 2 predicates and 17% 3 predicates.
Okay, well, the right answer was 2, so that's good. Okay, well, I talked about these graphs. Now, the question is, okay, so what languages, what tools do we have out there to create these graphs? And that's where the semantic web technology, sort of the stack or sort of layered cake, come into play. I'm not going to go through the details of this semantic web of linked data, but I would like you to kind of point out some of the technologies and frameworks that are there what I would like to emphasize, as we go higher on this sort of a stack model, we add more expressiveness to our models, to our semantic models. So as far as the languages that we can use, I'm going to go through the definition of what an ontology is the research description framework, the web ontology language. Also, we can use different query languages such as the Sparkle to kind of query against those models that we've already defined, and also define constraints and rules, using shackle, which is shape constraint language on those ontologies. So again, just a quick introduction of the framework and some examples. So the first layer, the first semantic layer that's not very expressive, is the resource description framework, RDF. Basically is a conceptual data model which can be serialized using various formats such as Turtle. So again, the format is the graph, but we can serialize it if that needed. So in this example shown in blue, this triple is defining cooling coil 1 and using a predicate from RDF that's called type. And coil is basically another concept that we're defining. So basically what we're defining, say cooling coil is of type coil in this triple statement. Now the next layer on top of RDF is RDFS, which adds more concepts to RDF and provide more expressiveness to the model to define a description between groups of RDF resources. So for example, here we can define that a coil, the concept of coil, the predicate again is from the domain of RDFS, and that's subclass. So the concept of coil is a subclass of a concept called heat exchanger. So that's how we're going to define our sort of pieces required in our model. Now, the other layer, which is a lot more expressive than RDFS, is the web ontology language known as OWL, which is a classification language, and it's based on the open world assumption. And by that, I mean, if something doesn't known to be true, it is not necessarily false. It's just unknown. And that can be of significance for a lot of industries. So they may need to know that. So again, as I mentioned, is a classification language. So we can define that a coil is of RDF type, but OWL class. As you can see, the namespaces of, sort of what framework or what languages you're using comes before, and the actual predicate or concept that you're using comes after that. And finally, the shape constraint language, or shackle, is a specific language. It's a lot more expressive than OWL, and it's based on the closed world assumption. So in shackle, if something is not known to be true, is false. So why are we using these technology for knowledge representation? I have listed 3 of them. There's self-describing models. They're easy to interrogate. By that means, query. They're easy for inferencing, and I'm going to go through examples of what that means. So self-describing models, I've used the word ontology for those of you who are not familiar with the term. Ontology is basically a formal and explicit representation of concepts and their relationship that's machine understandable. So it's like a schema, but talks about the concepts and the relationship between them that is machine understandable. So think of it, let's say that you want to design an ontology that talks about humans, animals, and such forth. So what you can do is you can define a concept called mammal, and you use the RDFS framework to borrow the subclass of predicate, and you define the mammal to be subclass of animal, and the human to be subclass of mammals. So I would like you to pay attention here that this ontology, we are only talking about concepts, right? So this is at the schema level. This is just the concepts and the relationship. And at the data level, which are the instances, we define specific instances. So for example, we're saying George is a human being, and A is kind of an alias for RDF type. So basically what we're defining is saying a specific instance called George is of type human. Also, we're defining another triple in this graph, and we're saying that George is married to Lisa. So notice that this married to is can be a predicate that you are just newly, freshly defining. You have defined in your ontology, and you're not using other ontologies to kind of reusing other ontologies predicate for this. So the second benefit was they're easy to interrogate. Sparkle, which is a Sparkle protocol and RDF query language, can be used to query the semantic graph. So we can use the Sparkle queries both at the data level or the instance level, and also we can use it at the schema level to talk about or ask questions about the actual ontology or schema. So for example, and the way the Sparkle queries work is basically pattern matching. So the way it works is it's going to select an X is just defined as a variable. Where in the graph, so we're going to go search in the graph, and wherever it finds this pattern of triple, so where there's a subject called George, a predicate called married to, it's going to take the object and return that to us. So since we have defined it in the previous slide, that George is married to Lisa through this predicate, over here, this is going to return a table and it's going to say Lisa. Similarly, we can use a Sparkle to query about the schema. So for example, let's say that we're interested to know the subclasses of the concept animal. Since we've only defined one subclass, and that was mammal, that's the only thing that's going to be returned. So again, here it's going to look for the pattern that has anything, the predicate subclass, and the object that it's of type that's of a class animal or concept animal. And it's going to return mammal to us. Lastly, it's easy for inferencing, and that's a very, very important feature here. As you recall, at the beginning of the talk, I was talking about the ability to do reasoning. So the ability to generate triple, to create new information based on what you have, is a very key point here. So for example, we as human beings, if we're giving the information that George is son of Fred, Fred is sibling of Mary, then we can deduce that George is nephew of Mary, because that rule is in our minds. So the question is, how are we gonna code that for our application to understand that? We can use a Sparkle, and the way we would use that, we would say, well, construct this triple pattern that A, nephew of C, so that's a triple pattern, where in your graph, in the graph, you see these two patterns. So where in the graph you see that A, the predicate son of B, and B is sibling of C. So wherever these two patterns are C, this one is going to be asserted to the graph as well. And that's very, very key here. And I'll show you through an example. Now, well, let's get to the building and see how we can use this sort of technology that I talked about and benefit us in the building and the different application for the buildings. So the first thing that we're going to do, we're going to implement a data graph that would kind of hold the facts about our system. So here's a very simple example. Look at these two rooms, room A, room 1 and room 2, and think that these two rooms belong to like zone 1. So the information we have here, that zone 1, which is the subject predicate, is served air handling unit 1. So that's the air handling unit that's serving to zone 1. We have the list of the sensors. So sensor 3 has location room 2. Sensor 1 has location room 1. Sensor 2 has location room 1. And then we're defining our HVAC or thermal zone. So zone 1 contains only room 1. Zone 1, not only room 1. Zone 1 contains room 1, and also zone 1 contains room 2 as well. And zone 2 only contains room 2. I mean, think of it that zone 1 is a heating zone and zone 2 is a cooling zone. And if we look at this data as humans, we can kind of infer that although sensor 1 and 3 are in 2 different rooms, but they belong to the same HVAC zone, something like that. And now let's see how we can use the Sparkle to kind of get the similar information as the way we would get it. So again, the pattern is to get us the sensor enclosure and zone. So we're going to query the graph for these 3 pieces of information. And we're going to ask it to go and find in the graph to find the things that are of type zone. So anything that's of type zone. And from that set, only select the zones that contains an enclosure. And from those enclosures, choose the subset that there is a sensor that has a location in that enclosure. So this is like at each step, we're kind of limiting the set and using a subset of that. And when we run that query, we're going to get the result of sensor inclusion zones. And you could see that sensor 1 and sensor 3, they belong to the same HVAC zone. And you could also see that room 2 belongs to different zones. So again, as I mentioned, these are just examples. It can be a heating zone and a cooling zone. So those are the pieces of information that can be inferred from these sort of tabular formats. Now, the question may be that, well, this is great, but shall we all make our own graphs and query those graphs, or what are the existing schemas and standards that can be used for different building analytics applications? So this is an interesting graph. Over here, it shows about the existing sort of standards and schemas, such as brick schema, project haystack, IFCL. There are more the real estate core ontologies, building topology ontology, and there are a few more ontologies that are out there that can be very useful for different building applications. On this side, it's more about the models about smart grid, which is not the focus of this talk. And in the center, there are some existing schemas and ontologies that are kind of domain agnostic, but we can use it certainly for building applications. For example, QUDT, which is an ontology that talks about quantities and units, the notion of calendar, the notion of the ontology for sensors, for weather, different models out there. And that's the power of linked data, that these graphs can be using each other and linked with each other to provide pieces of information for our different applications. And there is a newer effort supported by ASHRAE, which is ASHRAE Standard 223, that's currently under development. So the title is Semantic Data Model for Analytics and Automation Applications in the Building. And the purpose is to formally define knowledge concepts and the methodology to apply them to create interoperable, machine-readable semantic models. And when we have that, then we can use it for different applications in analytics, automation, and control. So that's the goal of 223 that's currently under development. And there are very specific use cases that we're going to use this model for, such as automated fault detection and diagnostics, control system configuration, building system commissioning, digital twins, optimization of energy use, energy audits, and smart grid interactions. Just an overview about this model. The focus is on topology and not geometry, although this model can be linked to other models that are very robust and rich in representing geometry about domain buildings. Telemetry data, that's information about the mode or state of equipment, is not stored in the graphs of 223, but certainly we can impose constraints on them. This model is going to enable us to integrate with other related models for the building, such as the building information model. 223 models the ground truth details about the connection between the devices, and that's one of the key differences with brick schema. And certainly this works on top of the pioneering work such as Project Haystack and brick. We will be considering to include the taxes that exist in the Project Haystack through a combination of concepts and properties in our model. And certainly we're going to capture information about spaces and zones without geometry, and that's the key part that we're going to do integration between the lighting and the HVAC system. So the benefit of ASHRAE 223, it integrates many standards and schemas needed for building analytics. It supports rich knowledge representation and reasoning to be used for building domains. And it reduces certainly the cost of integration and application development. And that's the key point for any standard, specifically this one. Okay, let's dive into an example. So here's a picture from Guideline 30, ASHRAE Guideline 36. And I would like to walk you through the process of getting from this to those ontology graphs. Now, at this point, this process is very manual, but I just want you to have an understanding of how this is going to work and how's that going to benefit us. So having this as schematic, we're going to then overlay the existing concepts. In this case, the 223 model, for example, we have a notion of device. So we're going to overlay the concept of a device on any equipment or devices that we see in the system. And then we have this concept of connection point, and we have a concept of connection. So we're going to overlay those concepts on to this graph, and we're going to then form that semantic graph through the subject, predicate, object, and kind of abstract those, get an abstract model of that schematic that's similar to a graph view. And then we're going to query this graph. So let's go through some examples here. Let's assume that this is the mixed air filter, and this filter is connected to other nodes here, which is this is the return damper, this is the airflow station, outdoor airflow station, and this is the supply outdoor air damper. And we would like to query the graph to see if, what is directly upstream of this filter. A lot of the times you may need to know that for your application. For example, knowing what's upstream of this filter may tell you if, you have a return system here. In a hospital situation, you may not have a return line here. So that helps certainly querying the graph will give answer to that question. So let's see how this is going to be, performed in a SPARQL query format. We're going to, again, pattern matching. First, find the node that has this mixed air filter as a subject, and then we're going to use the predicate connected from. So this predicate has been defined in our model, in 223 model, but this can come from a brick or any other model. So that's the key point, that we can reuse auto ontologies that are out there. And then from there, we're gonna get the object, which is the device. So when we perform this query, we're gonna get the result that the economizer outdoor air damper, the outside airflow station, the return damper, these are directly upstream of this mixed filter. And this is the result of just the portion of graph, sort of graph view of this result of the query. That's the subject, predicate, object here. Similarly, we may want to know if our system is blow through or draw through. For a specific application, you may want to know that if a fan is downstream of your coil or if it's upstream of the coil. So that can, provide some insight for some decision making that you may want to have. Again, we're going to search the graph and pick the part that's relevant to us and ask the question that we need the answer for. So in this case, we're going to ask where, ask the graph, search in the graph to find any instances that is of type coil. And from all those sets, we're going to search only for the ones that has the role cooling. Again, these are the definitions that are defined at the moment in 223. And then from there, we're going to transitively check any object that comes after connected to and check if they're of type fan. In this case, since our fan was downstream of the filter, the result is true, but also this query could be asked differently. So also we could have checked for all the devices that this this coil is connected from. And if it was a draw through, the response to this query would have been true. Well, so we looked at some examples, and let's see what the future steps are. We would like to complete development of ASHRAE Standard 223, develop a library of building models, sample building models that we can then, based on those, exercise and test the details of this standard. Definitely want to align 223 with other existing ontologies that are used for building analytics. And as I mentioned, this process of creating 223 model is now very manual, but hopefully we can have software tools that can automate the process, especially when it comes from the building automation systems or other systems such as BIM models. Would like to develop a reference model query set similar to the ones that I just talked about for different applications with the help of domain experts. We would like to have those set of queries that we can run against our model. Developing testing tools and processes for validating conformance. So if someone says, I'm 223 compliant, there's a way to validate the conformance. Hopefully, I was able to convey the message that semantic models are a great resource for representing the building knowledge needed to enhance building analytics. Using ontologies and rule sets will integrate data from non-machine processable sources, such as drawings, documents. And semantic models provide mechanisms to make decisions based on rich contextual information from various domains. And that's the key point. Semantic interoperability is the key point, that we can integrate information from outside environment, from occupancy, from our lighting system, from our building information and communication, from the building automation system, from our renewable resources, from the electric vehicle, all of that through this linked model, linked graphs. And then we can perform we can develop applications that would perform by using and getting information from these graphs. At this point, I would like to acknowledge my colleagues at NIST, Stephen Bushby, Amanda Perspon, Andy Persley, Daniel Veronica for Hodomer, and Kelly Kanangala for their valuable input, feedback, and mentorship. My ASHRAE 223P modeling team, especially Stephen Ray, he's my modeling partner, a great mentor. Joel Bender, the same. The IIT and UMD colleagues, Mohammed Haydar-Nejad and Mark Austin, for their valuable time and feedback and input for this work. And with that, I'm open to questions, and thank you so much for your attention.
All right, thank you, Parastu. This has been a very interesting presentation, certainly new to me and to many of us, I'm sure. I want to open the floor for questions and invite a discussion of what you've talked about. While people are taking some time to type their questions in the chat window, please go ahead and do that. I'd like to also ask, if you're watching us on our YouTube live stream, please take a moment to like this video and to share it. We really appreciate your views. While people are coming up with their own questions, I'd like to start with one of my own.
Sure.
Can you talk about what semantic modeling is like from the user's perspective? So are people going to be creating semantic models, or will our software just do that automatically? And will we be posing the questions, or is our software going to know how to pose the questions and come up with them all on its own?
Sure. Yeah. So there are different, that's an excellent question. There are some people who, depending on where you are in your profession, there are some people like us who will be developing those models, right? And there are going to be some people, it could be an FDD or some analytics company that will be using our models, but, they are going to write a layer of application that will be on behind this hood is going to use the semantic model, right? So the results of what they're asking for is going to be translated to some sets of queries that's going to be performed against the model. So there are some people who are going to directly use the model, and there are some people who are going to use the result of the model, depending on where you are. But ultimately, we hope that this complication of these models are going to be not visible to the end user. And so a lot of people who are developing those applications will be using the smart database. You can think of it behind the hood to kind of get to what they're looking for.
All right, thanks. We've got a question coming in from Nelson. He says, I see that the point of the abstraction from BIM to code to facilitate automation, but is the other way around also considered? Do you know of some examples where a cluttered filter is signaled in a BIM model?
So not at the moment. So what we're trying to do here as a first step to be able to get as much as information as we can in our semantic model, in the model that's going to be used for different applications, not the other way. But certainly that can be something that can be looked at in the future that goes from the other way. So for example, from here to the BIM model. But at this point, what we're going to use, hopefully at the end, we're going to use this to get the information about the topology of the rooms and the zones from the BIM model, and then infer, okay, this is the filter, and this is the room that's providing, conditioned air to. So that's where we're, getting the information from the BIM model for our own decision making, not the other way around at this point.
All right, thanks. We've got a question coming from Stephen. Stephen, would you like to go ahead and ask your question?
Hi, can you hear me?
Yes.
Oh, hi. Thank you for your presentation. Yeah, really good. And I'm really sold on this idea.
Thank you.
When I've tried it in practice, though, I've tried it on building data sets with large amounts of sensor data, time series sensor data. And the challenge I have is very quickly the RDF triples, you get lots of them very, very quickly, and the graphs become sort of unmanageable to query, really. And I just wondered if you'd come across that, you had any thoughts or solutions to that.
Sure. Well, thank you for the question. So that's the reason what we're anticipating and not storing the time series data in these graphs. So these graphs would only know the things that needs, for example, for air handling unit, you would know, okay, it has this property called supply air temperature, but you're not storing the time series data in the actual semantic graph, right? So, but this has a link to a database somewhere that will kind of knows what that is. And at the semantic level, you can also constrain, as I mentioned, telemetry data is not stored in our graphs. You can put constraints that this is the value, the valid range, this is what I'm expecting to see, but you're not actually storing the actual data in these graphs. And I agree that's going to be pretty big. So yeah, that's the hope that we are we're going to have that not storing the actual time series data in these graphs.
Super. Thank you very much.
Sure.
Thanks, Stephen. Here's a question from Haydar. The question is, how do you apply machine learning above the knowledge graph? So could you talk about the connection between this and machine learning? Okay,
well, I'm not sure if I have the right skill set, directly to answer, but I can, share my perspective. That's a good question. At least the way, again, this is just my perspective about this, not anyone else's. I'm not talking about any, the SOL 223 group people. So machine learning, if you think of it, learning and reasoning are two capabilities that we as human beings can do, right? We can learn things and then we can reason. So there are separate things, but kind of complementary to each other. One way I can think is the way that we are kind of creating these knowledge graphs are based on domain knowledge, right? But the ways, we go and say, oh, we see this concept, of air handling units, or kind of drafting these graphs from our own knowledge. One way to kind of do that could be using that categorization, using different machine learning techniques. So based on the data that you have, you kind of go through the data and categorize using machine learning techniques. You can categorize, oh, I see similar data, or maybe that represents a concept in the ontology, or maybe these rate data that you've performed classification machine learning algorithm of has some significance in my system. So you kind of mine the data to get different classification of data. Again, that's an interesting thing to see, in future. how we can tie and create a synergy between the two worlds. But at this point, we're not doing anything about that.
All right, thanks. I want to remind everyone, please, type your questions into the chat, and we certainly want to get through as many as we can. Here's another question. So it seems like, these ontologies coming through W3C could be applied to a lot of areas. Are there connections between using them in buildings and using them in other cases? Can we make connections with other disciplines?
Can you give an example? Yeah, sure. There are people are using ontologies in cancer research, right? And a notion of, for example, time, which I talked about in the donut chart, is going to be reused in different domains. So as I mentioned, there are units or quantity kinds. There are ontologies that are domain agnostic, but we're certainly using them for buildings. But there are some ontologies that are specifically for buildings, right? So real estate, the topology ontology. If you have a few, like a very specific example in mind, but from what I can tell, the whole promise of linked data is that these ontologies can be linked together, and that's the whole benefit of kind of integrating information from multiple resources for a comprehensive knowledge.
Right. So maybe that's a good connection there is with cancer. So if we were to talk about sick building syndrome, for instance, could we make connections between HVAC systems and health records of people occupying those buildings?
Sure. Yeah, that's definitely. I mean, I had in my slide, I had an information about occupants, right? It could be information about the performance or whatever. Yeah, definitely. So that's the whole purpose of using linked data models, that we can link these graphs together and to have a better understanding of what's going on and see the impact of one domain to kind of the other domain as well.
All right. Here's a question coming in from Hader. Do you recommend any software that can start with that we can start with to build our brick schema, for example, out of air handling units?
Sure. Yeah. If you look at the brick schema, I'm not an expert in brick, but if you look at, there are some open source Python libraries that you certainly can use, and I think Brick website has reference to that, and they do have examples that you can take a look. There are some sort of commercial softwares that are out there, and they're more of a sort of a editor visual. If you're not interested in coding, there are other softwares out there. I'm not planning to endorse anyone, but you can send me an email. I'll be happy to point you directly to other existing tools as well.
All right. And Heather asks one more question, which is there any course you provide about Semantic Web?
Just in general, I guess that the question is, I'm not aware of a specific course that could be like a sort of a, very detailed about, talking about these models, but I can certainly send some, if he can send me an email, I can send some reference materials that can be useful for educational purposes.
Okay. Matt Steen has suggested a GitHub repository, which is GT Fierro's OOMASON. I'm not so OOMASON, maybe.
Yeah, I think that could be a good for a resource for definitely brick configurations and creating a brick example. I think that's going to be, yeah, that's for brick.
And Matt Steen, I don't know if you're on here and want to, sorry, Matt Steen, if you want to go into any further detail on that. Don't hear anything. we'll see if there are any last questions coming in. Again, I want to thank you, Parastu,
Sure.
for the time that you've spent with us today. This has been really interesting, some very original work, and we're really happy to see work like this coming out of NIST.
Well, thank you so much for your invitation and giving us the platform to share our work with the rest of the community, and certainly hope that we get more people that are interested in this work. Come join us if you're interested, and kind of we all can work together and make it better.
All right. Well, thank you very much. I want to, again, thank everyone for joining us today. And I'll just close out with a few remarks. First of all, if you enjoyed this webinar, please consider joining the IBIPSA USA Research Committee. Email research@ibipsa.us or fill out the form that I've just pasted into the chat for everyone. For those of you who are joining us on YouTube, please like this video and subscribe to our YouTube channel. And please join us again on September 30th at noon Pacific time when Michael Wetter presents IBIPSA Project 1, New Generation Computing Tools for Building and District Energy Systems. All right, thank you very much.
Thank you.